So now building upon their insights, I will cover auto-label tools that assist in labeling reasoning datasets. Additionally, I will address the challenges of hallucinations in LLM annotations and discuss strategies to overcome them. Now let's see how can we generate synthetic datasets using large language models. Several tools have emerged that use LLMs to streamline this process. First, talk about the recent popular auto label tool. It's a labeling agent that provides method for generating synthetic datasets, particularly supporting tasks like classification. For example, sentiment analysis, emotion identification, these kind of tasks comes under the classification problems, and entity matching tasks like NER and coreference resolution. Auto-label automates the labeling process, enabling us to create large datasets efficiently. Then comes the Prodigy, which integrates LLMs into the annotation workflow. By allowing us to provide prompts to LLMs, Prodigy helps annotate NLP tasks more efficiently. This not only speeds up the annotation process, but also ensures higher consistency in the initial annotations. Then comes the label box, which is a platform that significantly enhances our data annotation process and helps improve our model annotations. It is very easy to curate and annotate the dataset using the label box. It generates high quality human feedback data for computer vision tasks and language models. And it can evaluate and improve the model performance. Lastly, LLM data annotation, which combines human expertise with the efficiency of LLMs like GPT 3.5. This tool simplifies dataset annotation and aids in model improvement by leveraging the strengths of both human annotators and LLMs. Collectively, these tools showcase how integrating LLMs into our data generation and annotation process can significantly enhance efficiency and quality. They help us overcome the challenges of data scarcity and pave the way for building more robust and accurate AI models. Now let's discuss about the auto label tool. Auto label is built on Refuel LLM, which is a recent LLM. And here, let's say we want to do the annotation for customer support tagging task. So first we need to give the task guidelines. In the task guidelines, you need to explain the LLM that what you need to do. In this task, which is customer support tagging, we are giving the guidelines to LLM that it should act as an expert, the support agents and customers. Here, the goal is to categorize the type of issue in the conversation faced by the customer into one of the following categories. So whether it's related to the warranty of the product or account login or shipping, returns, and so on. So here is our input in the structured format, which is nothing but our conversation. So here the customer and agent are conversing about some issue, like the customer received a wrong item in their order and he's talking about that. Once this conversation is given to the auto label tool, if we click on see result, it will automatically generate the annotation using the Refuel LLM as well as the GPT-4 model. Here you can see that clearly this particular conversation is related to the returns category. And also the models will give the confidence score as well as the time taken to produce the annotation. Now the question is how to use auto label tool to annotate for any given task. Let's see this with the help of an example. So here I'm explaining how to use the auto label tool for question answering task. First, you need to define the config file for any given NLP task. So in the config file, the task type is question answering and the label column is answer. And we want to use the GPT 3.5 model. So here we need to write everything in the model under the model settings. And then we need to provide the prompt. So these are the task guidelines, means how you want the LLM to act with respect to this particular task. And here are the few short examples. As Subba and Manish told, we can give the prompt in one shot, zero shot and few shot. In few shot, we can provide more than one example. So here we provided three examples where we provided the question and answer and also the context, why this answer is given. And this is how we created the config file. So this is the first step, which is specifying a label configuration. Then the next step is we need to create an agent for labeling. So for this labeling agent, we will pass our config file and also our test set. Then the agent will create a plan and execute this. So if you see this slide here, the total time took for the annotation is only like, the total cost is around $7 and the number of examples is 2000. And this is how your prompt look. So in the second step, we do a dry run on test dataset using the LLM specified in the config.json. So in the config.json, we specified GPT 3.5 by running the agent plan method. And the final step is to run the labeling with the agent.run method. So here we can give our own data and how many items are there for the annotation purpose. Here we have 100 items and the tool automatically generates annotations for all the 100 items and it gives some evaluation metrics like F1 score, support, accuracy and completion rate, how many total number of failures. In this case, we got 0 failures for this annotation. Okay, now the question is, can LLMs label the data as well as humans or faster? Let's see this with the help of these results. So in this slide, we can clearly show that this table summarizes label quality results across datasets. So what is label quality? Label quality measures how well the generated labels by humans or LLMs agree with the goal truth label provided in the dataset. For example, these are already annotated datasets. That means we have the gold label. And also we do human annotation and LLM annotations. We have three labels. First one is the gold label, second one is the human annotation labels, and the third one is the LLM annotation labels. So label quality measures how well the generated labels by humans as well as the LLMs compared with the original gold labels. Highest numbers in each column are highlighted with the green. So here GPT-4 is performing better when compared with the human annotations when we are comparing these annotations with the gold labels. And also reviewer LLM is also performing very well in the annotation process. And here they considered 15 such NLP tasks and they have verified with respect to human annotators and also with the recent LLMs. And you can clearly see that Refuel LLM outperforms trained human annotators, GPT 3.5 Turbo, Palm, and Claude across a benchmark of 15 text label datasets. Now, how the LLMs perform on train versus test set, on the held out test set. So held out datasets that weren't used by instruction tuning refuel LLM, but we don't know whether these datasets are included in the closed source models because they don't know, we don't know the details of how these closed source models are trained. But for the refuel LLM, they kept these datasets in the held out case. So if you see here, it's clear that GPT-4 performed well on even the held out data. And also Refuel LLM is also giving on par performance with the GPT-4 method. So the conclusion from this slide is Refuel LLM outperforms human annotators and all closed source LLMs excluding GPT-4. Now comes the next set of evaluation. So we have 15 different NLP tasks. So those tasks are divided into 4 categories. Classification tasks, reading comprehension tasks, structure extraction tasks, and entity matching tasks. So, and these are all the models which are involved in training and testing. So from this, we can clearly see that Refuel LLM outperforms all the current state-of-art LLMs for data labeling and enrichment, including GPT-4 Turbo, Claude, and Gemini models. Then comes the next set of evaluation. So here what they have done is they compared the Refuel LLM versus GPT-4 and Claude in different domains like e-commerce, recruiting, legal, trust and safety, as well as financial services. So even from these results, we can say that Refuel LLM is competitive or superior in terms of output quality compared to the current state of art LLMs. So in some domains, Refuel LLM is performing better than even GPT-4 as well. So now you all know that we have the interfaces available for all these LLMs. Then what is the need for these tools? Because if we use the tools, we can use different LLMs and compare the annotation performance of all these LLMs. Then comes the prodigy. In the prodigy, as explained in the previous slide, we can provide the prompting with respect to our downstream NLP task, and we can query the large language model, and the zero shot, one shot, and few shot responses will be generated with respect to the prompt and the given task. So prodigy will take the input of these responses and curate the data for efficient task specific modeling. So it's not a software as a service. It's a tool that you can download, install, and run yourself. And also you can run this tool in offline. So for security reasons and privacy reasons also, this tool will be very good. Like if you're working on any medical kind of data, it's better to use this tool where you can download it and run on your local machine. So we can also annotate vision and audio tasks along with NLP tasks using this tool. Now comes the question, which tool is better, AutoLabel or Prodigy? Here, AutoLabel currently supports chain of thought prompting and suitable for reasoning NLP tasks. So these labeling tasks spanning categories such as classification, entity resolution, matching, reading comprehension, reasoning, and information extraction. So it's better to use AutoLabel when compared with the other tools. So having explored auto-label tools that assist in labeling reasoning datasets, we have seen how these tools can significantly streamline the annotation process by leveraging the power of LLMs. Auto-labeling not only saves time, but also helps in scaling up dataset creation, which is crucial for advancing our research and application. However, while these tools offer immense benefits, they also bring certain challenges. One of the issues is the phenomena of hallucinations in LLM-generated annotations. Let's see the definition of hallucination and also the taxonomy of hallucinations. So what is hallucination? The experience of seeing something which is not there, the experience of hearing something which is not there. So these are all the definitions of hallucinations. Do LLMs hallucinate? First, when models generate information that is incorrect or nonsensical, means when the model provides uh, unrealistic information, then we can say that LLM model is hallucinating. In the context of language models, the generation of text or responses that seem systematically sound, fluent, and natural, but are factually incorrect, nonsensical, or unfaithful to the provided source input, then this is called the hallucination. How did hallucination evolve in LLMs? How the hallucination evolved in LLMs? Initially, in vanilla LLMs, we have a prompt. So here, the Prime Minister of United Kingdom visiting India. This is the prompt. In this case, the model is generating the text which is nonsensical. So the model does not have any information, but it is saying that they are visiting to strengthen the bilateral ties and exploring opportunities for collaboration. So this is all not correct, but still the AI model is generating. It simply generates text without knowing the specific details of the visit purpose. Here is an example of GPT-4o hallucinated when asked, "Are you sure?" So from the figure, we just uploaded the time, what is one clock image, and we asked the multilingual multimodal LLMs, what is the time in the clock? And the LLM generated the response as the time on the clock is approximately 1.25. So then again, the user asked, "Are you sure?" If the same question is asked to the humans, they will say, "Yes, it's sure," and the time is 125. But here the LLMs gave a different answer saying that the time is 8:20. So despite advanced capabilities of multimodal LLMs, like all LLMs are prone to hallucination. The problem of hallucination also exists in all foundation models like image-based models, video-based models, and audio-based models. You see this example here, we use the GPT-2, the mini GPT model, and by seeing this image, the model generated a person in a white shirt and dark pants is standing outside of a building. But here there is no building. But the model predicted that there is a building, which is an alarming hallucination. Then comes the second picture where the model is unable to identify the person in the image and it mistaken with other co-founder of Google. Now I would like to discuss the different types of hallucination that occur in large foundation models. So the hallucinations occur in large foundation models in almost all the modalities like text modality, video, image modalities, video modalities, and audio modalities. So even in the text, it occurs in all the LLMs like multilingual LLMs, domain-specific LLMs, and multimodal LLMs as well. Yeah, like the conclusion from this slide is like the text-only counterparts in LLMs, video and audio-based language models are also prone to hallucinations. Now, how actually hallucinations occurs in LLMs? When we train LLMs, we feed a lot of data and train these LLMs. What if the data is not correct? This means whatever the model learns, it is false information, which becomes a source of hallucinations. Data quality relevant hallucinations occurs due to noisy data, lack of diversity, and so on. So the hallucinations can occur from data. Similarly, the hallucinations can occur from models, and the hallucination can occur from when we are training the models and at the inference stage as well. So when we have Yeah, to evaluate the LLMs, we have different benchmarks. Like when Subba and Manish explained, they talk about the benchmarks like MMLU, and we also have the other benchmarks like Helm, Big Bench, and so on. To evaluate these hallucinations also, we have several metrics and benchmarks. For example, these metrics were designed for object identification. So the chair is a hallucination metric proposed to evaluate object hallucination task in the traditional image capturing task. Also, we have the discriminative and generative task related hallucination benchmarks. So we have seen the primary causes of hallucinations, the metrics and benchmarks, right? Now the question is how to mitigate these hallucinations. For mitigating hallucinations, recent works make attempts on data, including introducing negative data like counterfactual data and reducing noise and errors in the data set. That means balancing the data and also balancing the model related hallucinations by using dedicated modules and scale up resolution and mitigating the training related hallucinations and also inference related hallucinations. So these are all the 4 steps that people use to mitigate the hallucinations. So having examined the taxonomy of hallucination types along with their causes and mitigation strategies, we built a foundation in understanding how hallucinations how hallucinations affect LLMs. Now let's delve deeper by exploring hallucination types from 3 additional perspectives like orientation, category, and degree. This will provide us with a more detailed understanding of how hallucination occurs and how to detect them. The 2 primary orientations of hallucinations are factual mirage and silver lining. So these 2 orientations are classified into 2 types, intrinsic as well as extrinsic. And these 2 are further classified into 6 categories: time wrap, geographic, erratum, and so on up to acronym ambiguity. Then comes the degree. So these 6 are divided into 3 degrees, which are mild, moderate, and alarming. The conclusion from this slide is hallucination can occur in any NLG task, necessitating a thorough examination based on the fundamental principles of text generation from a given text prompt. Let's see all these types with the help of an example. So what is factual mirage? Factual mirage occurs when an LLM engages in hallucination of a given input that is factually correct. So this is an example of intrinsic hallucination. The LLM is providing a correct response while adding an additionally supplementary fact saying that the world fashion capital. So the question is capital of France and the age generated text is Paris with some additional information, but the actual fact is just Paris. This is an example of extrinsic factual mirage. So the prompt is engineering effort to build Eiffel Tower. So here it refers to the phenomena where an LLM deviates from factual answer. So the factual answer is it is built to celebrate 100th anniversary of French Revolution, but it gave some other answer. So to celebrate the anniversary of European Civil War, which comes under the case of extrinsic orientation. Conclusion is the generated text that appears to be true or real, but it is actually misleading or false. Then comes the orientation. So what is meant by orientation? So in orientation, we have 2 types. In silver lining, we have again 2 types, intrinsic and extrinsic. Let's talk about the silver lining. It's an LLM indulges in hallucination by conjuring an elaborate and captivating narrative based on a given prompt that is factually incorrect. Let's see this with the help of an example. So in the intrinsic silver lining, it's a category when some cases LLMs does not generate a convincing story. When an LLM generates a highly detailed and persuasive narrative in response to a factually incorrect prompt, then it is called intrinsic silver lining. If you see the example, here it generated some answer related to the given prompt, cell phone numbers go public this month. But the fact is this whole statement is false. Then comes the extrinsic silver lining. When an LLM generates a highly detailed and persuasive narrative in response to a factually incorrect prompt, it falls under the category of ESL. So here Kamala Harris and Elon Musk are getting married. This is absolutely the wrong, but still it generated a narrative kind of response for this false prompt. So in this case, the fact is the incident never happened. This comes under the ESL, extrinsic silver lining. The conclusion is LLMs provide unfaithful content or is inconsistent with the provided source prompt. Then comes the category. In the first talk about the time wrap. Time wrap is the LLM generates the text that exhibits a matched fusion of events from different timelines. Let's see this with the help of an example. So here the US president during the Ukraine-Russia war is Joe Biden. not Barack Obama, thus contradicting the factual reality. This comes under the time wrap hallucination. Then comes the geographic erratum. So here the LLMs generate an incorrect location with an event. So let's see this with the help of an example. Here the Prime Minister of United Kingdom visiting India, but the AI generated text contains a location which is Pentagon, which is not existing in the in India. It's the defense headquarter of the USA. So here the LLM generated the hallucination with respect to the geographical location. Then comes the virtual voice. So here the LLM generates quotations attributed to either fictional or real characters without sufficient evidence to verify the authenticity of such statements. Here we have given some prompt related to the COVID-19 vaccine, and the AI generated this particular text. Here the fact is, Pfizer CEO never said this. So this expression, giant leap from humanity, is quoted from Neil Armstrong, renowned historical statement upon stepping onto the moon. So the AI generated text used that statement to answer this question here, which is incorrect. Then comes the generated golem. Here, the LLM fabricates an imaginary personality in relation to the past event without concrete evidence. Here, the prompt is earthquake in Turkey, but there is no evidence that there exists a person, Hassan. But the LLM generated the text about the Hassan, that he rescued the survivors and helped them and all. So, but this is the false thing, which is related to the generated golem. Comes the numeric nuance. So here the LLM generates numeric values related to the past events such as dates, ages, or monetary amounts that are inconsistent with actual facts. In the example showed by Subba and Manish also, we got lot of errors when the LLM talks with the numeric values. Even the chain of thoughts reasoning is giving wrong answers in most of the cases. So this is an example. If you give a prompt like Twitter is said to have laid off more workers, so the AI generated some text which said that the Twitter reduced the force by 8% and roughly 600 people. But the fact is Twitter only laid off 200 people, which is roughly 10%. Then comes the acronym ambiguity. So LLM generates an imprecise expansion for an acronym. So let's see this with the help of an example. So the prompt is RLHF in reinforcement learning. Here the actual fact is it stands for reinforcement learning from human feedback, but the LLM gave a response saying that reward free learning from human feedback in reinforcement learning, which is not correct. So these are all the different categories where the LLMs can hallucinate. Comes the degree. So we have three kinds of degrees annotated as alarming, moderate, and mild. So the mild indicates minor hallucination, which is superficial in terms of its impact. The moderate indicates the level of hallucination that introduce facts that are either fictitious. And the alarm indicates added information pieces that bear a radical resemblance from the topic fed via prompt. The conclusion is now we know these are all the different kinds of hallucinations. How can we detect and evaluate LLM hallucination across different types? So let's talk about the first work in this direction. I mean, the recent work in this direction, which is hallucination detection using self-check GPT. So as the time is very limited, I'll go through only one method in the detection and one method in the mitigation, and I will conclude the session. So the other slides you can use from the website, you can download and go through the other slides. Yeah. So till now we have seen different types of hallucination and their categories like intrinsic, extrinsic. And now how can we detect such hallucination? One such popular recent work in hallucination detection is self-check GPT. So what is self-check GPT? It's a sampling based approach that can detect whether responses generated by LLMs are hallucinated or factual. So what is the motivating idea here? So the motivating idea of self-check GPT is that when an LLM has been trained on a given concept, so let's say the LLM GPT-3 is trained on some concept, the sample responses are likely to be similar and contain consistent facts. However, for hallucinated facts, stochastically sampled responses will give different answers. So because these are hallucinated, these are not facts. In one case, it may give that he is an Italian painter, and in other case, the LLM can generate that he is a violinist. So here, because we are getting all the hallucinated responses when we stochastically generate the responses from a given LLM. Like this, we will generate n responses. And these responses are likely to diverge and may contradict with each other, like we have seen in sample 1 and sample n. By sampling multiple responses from an LLM, one can measure information consistency between the different responses and determine if the statements are true or false. That means whether the statements are factual or hallucinated. Since self-check GPT only leverages sample responses, it has added benefit that it can be used for black box models like the recent LLMs, and it requires no external database. So the results suggest that this table shows the results and the performance of self-check GPT. Results show that the probability measures from LLMs generating the text are strong baseline for accessing the factuality. Factual sentences can be identified with an AUC PR, like area under curve with precision and recall of 53.97%, which is significantly better than the random baseline of 27.04, with the AUC PR for hallucination detection also increased from 72.96 to 83.24%. We can conclude that self-check GPT can efficiently detect hallucinated sentences with higher accuracy compared with several baseline methods and also with the random-based method. And also self-check GPT's prompting method achieved the highest performance in detecting non-factual sentences. The second work in this direction to detect the hallucination is fact score. So here you can, I'll just briefly go through this. So here, it's a new evaluation that breaks a generation into a series of atomic facts, which computes the percentage of atomic facts using some existing known database and says whether this is the factual information or non-factual information. Here we have two key ideas like atomic fact as a unit, and the second is factual information precision as a function of the given knowledge source. So the results show that GPT-4 and ChatGPT are more factual than public models, and Vicuna and Alpaca are some of the best public models. Then comes the hallucination elicitation dataset. So to evaluate hallucination, we need benchmark datasets similar to how LLMs have. So here to construct this dataset, we have utilized two primary sources of data, which is like New York tweets, which are factually incorrect, and the political dataset where we have factually incorrect, which is nothing but the silver lining. 15 LLMs were selected and used them to generate a total of 75,000 text passages, with each LLM producing 5,000 text entries. And they also annotated this with the help of Amazon Mechanical Turk. So this is how they created the dataset, and they also so given the ever evolving nature of the field, this benchmark leaderboards will remain accessible to the research community, fostering an environment of continuous updates and And then comes the hallucination vulnerability index. So now we have the data sets and we have the methods to mitigate the hallucinations. We also need a metric to measure the hallucination. So using hallucination vulnerability index HVI, we can measure the hallucinations. In the figure shown left, larger LLMs. So larger LLMs without reinforcement learning are prone to both orientations of hallucinations as shown in this figure. So to inspect the categorical changes in hallucination behavior of a particular LLM, please refer to the vertical axis of hallucination spectrum. So numeric nuance and acronym ambiguity are mild hallucination categories showing the reduced cell orientations as LLM size grows. So for smaller models like T5 and Dolly, so we can clearly see that generated golem and virtual voice and geographic erratum categories of hallucinations are rarely observed. So from this, we can conclude that larger LLMs without reinforcement learning are prone to both orientations of hallucination. And for smaller LLMs like T5 and Dolly, we have these category of hallucinations are rarely observed. So now the last part of this session is how to mitigate hallucinations. So as of now, we have discussed how to detect the hallucinations. Finally, we will see how to mitigate the hallucinations. So this figure shows the proposed approach for addressing LLM hallucination problem. So given an input, here the input is write an article on Rick Mahler. So the model will generate some text. So given any input, we iteratively generate the sentences from the model and actively detect and mitigate hallucinations. In the detection stage, we first identify important concepts. So here the important concepts are Major League Baseball, picture, 1953, Jupiter, Florida. So these are the identification of the important concepts. And calculate models uncertainty on them and then validate the correctness of uncertain concepts by retrieving relevant knowledge. It's like a RAG based approach. So using the existing knowledge, we will say whether this fact is correct or not, this fact is correct or not. So like that, we will validate whether these facts are correct or not. So we repair the hallucinated sentences using the retrieved knowledge as evidence. Finally, we append the repaired sentences to the input and continue generating the next sentence. So this is a continuous process. We show that this procedure not only mitigates current hallucination, but also prevents its propagation in the subsequently generated sentences because we will correct the initial sentences. The graph shows that comparing the percentage of hallucinations on article generation task in the output of GPT 3.5 and the proposed model is better. The lower is the better score here. So the proposed model is better here. The conclusion is proposed activate detection and mitigation approach successfully reduces the hallucination of GPT 3.5 model from 47% to 14% on average. So the next work is using chain of thoughts. This I am, please go through this as the time is very less. So the conclusions is chain of thought verification also reduces the inaccuracies in LLM responses by verifying the facts through the structured question answering. So in this way, first it will create the structured questions and it will verify the facts. Then this also reduces the significant reduction in factual hallucination and the final responses are more reliable and factually correct. So then comes the final question, is hallucination always bad? So what do you think? So one of the opinion is hallucination is not that much bad because so here recently also the researchers mentioned that the hallucination is good when we are using these models because we can improve them, and also some of the benefits is hallucinations creatively can lead to results or novel combination of ideas that might not readily occur to most individuals. So the hallucination become problematic when the statements generated are factually incorrect or it generates unnecessary information which creates some harms to the cultural or particular individuals. So this is especially critical in situations where an individual relies on LLM to provide expert knowledge. And these are also the few cases where we can see the improvement is there. Like in numericals, models have been shown to hallucinate a lot while generating numericals such as dates, quantities, and scalars. This is what we have seen in today's session. And in the long text, like models often tend to self-contradict while generating the output. Let's say here, if you want to take an entire Reddit conversation, and if you want to give labels for each post, let's say the Reddit conversations are 590 comments long, and each comment is very lengthy, ranging from half page to full page. In this case, we have a lot of phenomena like lost in the middle, recency bias, and all. So in this case also, the models need to improve a lot, and the reasoning. So these models are misunderstanding the facts or information present in the source text and can lead to the hallucinations and errors. And the next is when the contextual knowledge conflicts with the parametric knowledge. So here also we have seen in the previous sessions that why we are getting hallucinations. So models have been shown to prioritize the parametric knowledge over the contextual knowledge, which leads to the hallucination. So thank you all for your time. The tutorial code and material can be accessed using this link, and this link is also presented at the KR site. Thank you all for your time. If you have any questions, you can ask at the lunchtime.